Okay, so it's a pleasure to have you here, and we are basically officially starting our seminar, ROMER Talks seminar. Is this season 4? I don't know, I lost track. So Sinan has earned his BS in Electrical and Electronics Engineering from Ankara University in 2017. Following graduation, he worked as a design engineer in the defense industry until 2019, where he contributed to projects on autonomous UAV, swarm intelligence, and navigation in GPS-denied environments. Since October 2019, he has been pursuing a PhD at Université Libre de Bruxelles, Belgium, where he is jointly affiliated with the AI lab and the control design and systems analysis lab. His research focuses on swarm robotics, network control systems, GPS independent navigation, and unmanned autonomous systems. I have been we met I think last week, right, Sinan?
Yeah.
And he'll be defending, I guess, in November.
Yeah.
In November, and I'm part of his PhD committee actually. And his recent work is also published in Science Robotics. So I'm really excited to have him here.
Thank you very much. Thank you for having me here. It's a really great pleasure before my real PhD defense, so I have a chance to present some of the works here. Today I'm really talking about robot swarms, different kind of robots, UAVs, ground robots. So let's start with some basic terminologies, I guess. Is it working? No? Click here. Okay. So let's start from some of the basic terms. I guess most of you know what swarm robotics, swarms, but it's kind of interesting to know some of the details. This is an idea, swarm intelligence. This is an idea that simple local interactions can create complex, kind of useful global behavior. Think like ant colonies, bird flocks. In these creatures, no single ant or bird has a full plan. They don't know what they do really. So yet they together solve some kind of complex problems like coordination, routing problems. In that creatures, in that colonies, each individual has limited sensing and short-range communication capabilities. And these systems naturally, what we call robust, thanks to some redundancy. If one of their unit fails, the rest of the members in the swarm can keep going. So they don't exploit any kind of centralized control or hierarchical control. So like I said, there is no global map, there is no leader. So these properties kind of standard in swarm intelligence, but as you may understand, I'm trying to go a little bit beyond that. Swarm robotics is a little bit different than intelligence because now we are trying to implement those principles to embodied platforms. So we borrow those principles and try to implement in man-made, human-made robots. So our goal is to have similar properties of swarm intelligence like robustness, scalability, resilience to loss of any members, and try to have some useful properties and implement them in our real world applications. I said useful because usefulness is kind of related controllability. You know, we are engineer these robots, so we need to use them and also control them because we want to achieve some tasks. So robots should perform those given tasks. Tasks are given from us, from a human. So the swarm robotic research area has been there like 20 years and so. To control the large number of robots, we need to have, we don't get rid of some of the important properties like robustness, scalability, like I said, and some security against external attack, like adversarial behaviors. Okay, so basically there are two basic ways to control robot swarm. One is well-known centralized control, and the other is what we call self-organization. Centralized control, it is, we have lots of experience designing those kind of systems, centralized systems. And it is easy to program, but they have a single point of failure, and it's kind of difficult to scale. Self-organization is, as we observe in the nature, it's wonderfully robust, scalable, yes, but there's a problem, what we call macro problem. It's kind of hard to tell. Like I said, in self-organized control, we observe this problem appears in macro problem, and this is related to the problem is we want to program, we want to have emergent behavior, but we need to program single robots. So it's hard to guarantee that simple local rules will produce the exact global behavior we want. So we don't know. We can't trace. We can't have analyzable, tractable, traceable methods. So the problem is, like I said, we can only program a single robot. So and we try to go some specification related to what we want to do, and we wait. It happens or not. It's not so that guaranteed. So historically, what has been done is very empirical, as you understand. There are two lenses to program self-organized robot swarm. One is bottom-up. You design local interactions, rules, and you hope emergence gives what we want. And the other is a top-down. You specify the desired global pattern and synthesize rules to achieve it. You have some kind of optimization, task allocation, algorithms, patterns, machine learning patterns. So basically, you follow this loop. You design behavior, you test in your simulation. If you are happy, so you go to robots and try to realize what you saw in simulation, because there is a simulation reality gap. So you again try to adjust some of the behaviors in real robots. If you are happy, that's all. So this is kind of trial and error, and most of the designers in that area having hard time to achieve a new behavior. They're kind of classified how to program the behavior. One is the machine learning they also call evolutionary robotics, which is a kind of machine learning, and another type to get that behaviors is bio-inspired programming. That means you look nature and take inspiration from some of similar behavior, and you try to perform those behaviors. And the third one is kind of common. So it's a standard programming. You give the task to PhD students, and you say, okay, you find a way, and the students find a way to program. So they call standard programming. So up to now, we have seen a great science, and we used different kind of robots, some coin-size robots, or other kind of capable robots. So, and what they do is the basic thing. Some of them try to automatic design algorithms, machine learning. This one is try to draw a Christmas tree, and the right one is programming. When you give a task a PhD student, they do this. So this is what we have seen recently. So and to make things or realize things in real-world problems, we still have some open problems. And first of all, we still know how to solve that micro-macro problem in general. And also, we don't have any efficient way to interact with this swarm world, because the systems are distributed, and you don't have a robot to talk with. And additionally, when we talk about swarms, we are saying that like they are robust, they are fault tolerant because they have many robots. So, but in the actual world, one of the robot breaks, and what happens is the broken robot can get in the way of working robots. So there is no real adaptiveness or fault tolerances. We are just saying that they are given because of the swarm intelligence. Well, sorry. So what we did in past years, really asked ourselves, the thing is to make things enable for real world applications. We had a workshop from some of the people within swarm community, and ponder upon breaking some stereotypes, and actually what we have seen in last 5 years, we kind of relaxed some of the stereotypes in swarm robotics. So, for example, should our swarm, the first question we have asked was should our swarms really be autonomous? Probably they need human collaboration, because we want to do something with them to resolve some of our problems. So we need to collaborate them. So we need to communicate with them. So human input and the interaction with the humans control and monitor actually is kind of necessary. And the other question we asked, should we have large number of homogeneous robots? So, and we replied that like, well, it depends on the application and the context. if you can have large homogeneous or small capable heterogeneous robots. So, and the other thing we relaxed is like we were thinking like the robots should be incapable or kind of inefficient from the other counterparts like single big robots. But actually a lot of biological system we observe takes, and we observe and having taken inspiration from they are very capable, you know. So and they really understand their local environment, and they are able to do things individually, and we can't even do with our robots, you know. They are quite capable. So so we thought that the capability can be increased in those kind of robot swarms. Right. The other thing we have relaxed is hierarchical control. This is the main topic of this seminar. Just I told you there are two different control ways to swarms. One is centralized, the other is self-organized. But we observed that I will give some examples. Hierarchy can offer swarm robotics easier and faster behavior design, and also give a way to manage with more flexibility, you know, because it can able to us combine some behaviors. However, not just any hierarchy suitable to have swarm-like capabilities like scalability, flexibility, fault tolerance. The swarm members must autonomously create that hierarchy, you know, and they also should reorganize that hierarchy. So actually, this self-organizing hierarchy has been identified as a key challenge in swarm robotics in most recent surveys and the conference we held in Japan with the some automatic design and behavioral heterogeneity. So what I do actually in my studies, I partially integrate hierarchical control into a self-organized system through introduction of reconfigurable hierarchical layers. So we are going to go in detail after what is hierarchy. There are very different explanation definitions related to a hierarchy in the context of different research area. You know, you can find it on Wikipedia or Cambridge Dictionary, even in the some social science areas. But we don't have enough in understanding the reason behind why the this kind of multi-level hierarchy exists in the nature, and why we even us design some of the systems in a hierarchical level. So it turns out from our more strict investigations, we usually talk about the hierarchy in situations which entities can be classified into levels in a way that the other elements in the hierarchy determine some of the behavior or constrain some of the behavior. We find ourselves, the hierarchy actually is really about control of the behavior. But here we are not talking about a rigid organizational chart. We're talking about it's a rooted multi-level overlay, that can be created, reshaped, or abandoned on the fly. So the parts of the swarm can assume or cede their authority based on the local context, and this authority can be recoverable. So here we came up with a new definition of hierarchy. Like a hierarchy can emerge as a result of outcomes of competitions between pairs participating in the swarm. So this is a kind of self-organized way. Okay. Why does hierarchy matters? Actually, it gives what we observe in the nature is it gives better adaptability, more efficient and robust stable structure, better controllability, and the faster spread of relevant information. You can see there these are two Nature publications. One of is related to pigeon formations. They are the authors observe the GPS tracks and how they behave, and they come up with they observe that the pigeons has this kind of hierarchy, and the other is the dog shepherd context. So when we have a leader in the swarm, you can manipulate the swarm where you wanna go. You can define the direction. So these hierarchical advantages are actually related to collective motion. Like just we saw there, like a formation control. Well, what we did about this in our lab, we came up with the idea that robot hierarchy, we want to create a self-organizing hierarchy, and so we have a single robot. We have a swarm as if we are programming as a single robot. So think this is the diagram illustrates the what we call robotic unit, and it has some CPU, some sensors, and each individual robot has own CPU, and we call it brain unit. So when you introduce another robot, it merges and cedes its authority to other robot. So it's something like I was giving my hand, and then and you hold my hand and taking my control. I still have brains, sensors to observe, react the environment but you kind of controlling me. It's something like this. So here we have two different swarm. It has both have own brain unit, and they don't know the underlying graph of each other. So for instance, the robot D goes there and merges with the other swarm. It cedes to authority to robot B, and what we see here now they are creating a new structure, a new swarm. So the robot A, the new brain of the new swarm. So we have. So for instance, are they working? The robots are individuals here, so they are each of the robots can be considered a brain. So they are reacting stigmate repellent, and they create a new swarm here, and they also can retreat the agent here, the other agent. So they trying to merge in a single, what we call mergeable nervous system. So they create a new swarm. So within this new swarm, they also react collaboratively. So they are ceding their autonomies, but individually they can also react the environment. Here again, they start as individual and create a new robotic swarm. And for instance, here the brain has failed, and the other children understand that our brain has failed, and they are trying to search new elements in the environment, and they found a new one, and they created another swarm there. So they are kind of robust. Okay. So we demonstrated, this is also empirical trial and error, and we demonstrated the practical effectiveness. Yes, the self-organized hierarchy can work. We saw that, and but the problem is, in real world, you have faster vehicles, so like agile drones, ground vehicles, and what we have been dealing in swarm robotics community, we are dealing with some small and slow robots. So it needs a new design, and it also needs some kind of guarantees for stability and controllability. The other problem we haven't dealt in that work is extension of that concept to not physically connected robots. So wait. To make the concept applicable to real world robots, we need to have some systematic and mathematically analyzable organization and reorganization of the hierarchical networks. So we came up with the idea based on ideas related to graph theory tools. Since you know that swarms are networks, and the hierarchical systems based on graphs. So and they can be considered complex networks. So hierarchy also offers advantages for collective motion. So what we can do, we can design new graph theoretical tools to create those hierarchy, to establish a new reconfigure that hierarchy, and we applied we applied this idea into the formation control setting. Well, our goal is create a network that network operations actually that can construct and reconstruct the existing network with only local sensing and communication. Here we have two main questions to deal with. The first one is how we can create, construct a hierarchical graph. The other thing is how we can preserve the hierarchy during some tasks related to formation, like something like merging different graphs, robot departure from the graph, or splitting the graph into two. So what we do, we stack robots in layers. Each follower here, each follower has two parents. This is the minimal structure, what we call a minimal structure. The C there is child. The other P1 and P2 is a parent 1 and parent 2. And this kind of structure gives a matrices, what we call as lower triangle. It gives a way to simply define and control the network. The hierarchy itself, based on something we called Hannenberg construction. It starts from a small seed, like I just show you a minimal set of robots, and adding edges and vertices while preserving the rigidity. We have some bearing rigid structure there. So why this bearing rigid important, or what gives us for our robot swarms? Actually, the structure itself, what we call acyclic, and naturally match the leader-follower setup. So leader-follower setup gives us a way to interact with the swarm. And like I said, most importantly, the underlying matrices on these graphs stay lower triangular, so you can preserve the bearing rigidity and also design some new controllers. Since we have some ability to merge and split structures, we have some configuration safety. When we add vertex or edge, since the structure is bearing rigid, you can have guaranteed formations. We use bearings to ignore distances, so you can merge formations of different sizes. This is important, and different sizes and different structures. So we are decoupling the scale from the shape. Also, we are avoid some failure modes. So these are some of the examples here. At the left, you can see two different graphs, two different swarms are coming together and creating some edges based on our algorithms, the hierarchical construction algorithm. They are creating a new hierarchy, so they preserve rigidity and this gives us some useful properties we are going to see later. The other is the splitting one. This is the reverse operation of merging. And we have robot departure here. When a robot departs or fails, nearby agents, nearby robots locally maintain the rigidity and they cover the role of the failed robot. So they can, the task continue without replanning. Well, we demonstrate this approach in the simulation settings. First, you can see the navigation simulation here. They start random places and they create a cubic structure, and they can shrink or can get big on the fly. So this is thanks to bearing rigidity. Here you can see two different swarm. They have different sizes, but since the bearing rigidity doesn't care about the distances, they can naturally merge and have a new shape. The other is the splitting. Splitting is the same, and the at final at the bottom right you can see fault tolerance. Here an inner node fails, and the system runs the inheritance rule and quickly stabilizes the swarm. Well, what we had here, we enabled to self-organized control, hierarchical control, with most importantly mathematically provable properties, and we induced a Neve construction method, what we call hierarchical Hennenberg construction. Now, the final problem is extending the ideas to kind of faster, bigger, heterogeneous teams of aerial robots. We set it up the theoretical base. We start with some rough ideas in 2017, and we observed that these self-organized hierarchical structures can be helpful for designing some robot behaviors. Then we design some mathematical tools to have analyzable and provable properties. The final phase is the having wirelessly connected robots, heterogeneous robots, bigger robots, to reflect the real world constraints. So in this study we have published in Science Robotics, we worked on drones and heterogeneous swarms of drones and ground robots. Ground robots still slow, kind of slow, the PyPack, well-known PyPack. And we designed a new drone for our experimental purposes. It has time of flight sensors, external flight computer, external computer, and 4 down-looking cameras to localize itself. We used the swarm intelligence properties like onboard localization and communication. Then we came up with this structure. Here, this diagram shows who leads, who senses, and how the feedback closes the loop across the ground and aerial robots. In this setting, it's a similar setting. Actually, it's a similar setting in our previous work. Each robot consider itself as a brain, and everyone has the information of the initial target of the formation. But when they, for instance, let's say when they meet somewhere, they are trying to claim the authority. So, for instance, this drone claims the authority of 3 grand robots, and this drone claims 3 grand robots, 4 grand robots, let's say, and they can merge. So you can merge it like we are creating a hierarchy based on the hierarchical Hannenberg construction, and we see that the brain, the authority of the brain. Here we have a large swarm. We have just one brain, but it's not like a classical centralized control. This authority can be interchangeable, and if it fails, they can claim the authority. You can remove the connections on the fly, so they can preserve the hierarchy on the fly. And each of the child robots has still has own local goals, so they can control their sensory information and pass that information to the brain. Brain then gives some global goals to the children. How they localize themselves? Actually, we are. You can see the illustration of the tag-based localization. Since we are not a computer vision scientists, so we used some very well-known approach for localizations. Here, a drone detects an April tag, and it rotates and translates its own coordinate frame. If the 2 drones simultaneously detect April tag, they can exchange information, so they can know each other via this April tag. Also, they also have information through their sensors about their environments and the other robots. Like I said, they start with individual brains, and they are trying to recruit each other to populate the map in their memories. So one by one, they populate the map to each other and create the given formation. And they reach a target formation. The other property is interchangeable leadership. The brain can be changed on the fly, like this, and the other important property is explicit inter-system reconfiguration. Oops. Okay. All right. It's not working, no?
So if you have 2 brains, who gets to be the boss? It's just random?
No, you can approach that problem from different perspective. Now they are generating random numbers. So if the one of the random number is smaller, it's going to be cede its authority to the brain, to the brain.
It's just random, like one of them is picked as a
Yeah.
as the ultimate.
And they can also use some game theoretic approach to cede the authority. But for the moment, we went with the basic one. They are generating random numbers and they're playing that game. And if the bigger number, if this one generates bigger number, it wins.
Okay. So if I have two brains
Mm-hmm.
and they all have recruits, one of them comes, but they also have an imagined role in the final configuration,
Mm-hmm.
right?
Mm-hmm.
And they merge, then maybe do the brains change their imagined role in the big picture? Because they have to, right?
It's worked like this. Let me show you. For instance, like you said, it has information about, like, I am the brain, and I know the whole structure of the graph. When it sees authority, it knows the rest of the swarm, and it thinks I am the leader of the rest of the swarm. This is how we design. You have, if you have n number robots, you have n minus 1 leader follower structures. It's something like this. They are not giving up the idea of I'm the leader, so they have still the idea I'm the leader, because it's necessary, because when some of the parts fails, they need to have that idea. They need to have that authority. I'm the leader. So they know just the outsprings. I know they know they two robots. For instance, when we disconnect this link, and this is going to try to recruit, let's say, 10 more robots, because the initial graph has 10 robots. This is how it works. And you can see some of the reconfigurable behavior structures while they are navigating in the environment. Since they have own local sensors, they can react, but the global goals don't change. But if something needs to change the global goal, the brain robot decides. Well, let's go to real experiments. So we had, since we have a constrained environment in Belgium, we don't have such facilities like in ROMER here. We had to use 3 drones and 10 grand robots. So, like I said, they have targeted zones. Oops. Is this a different video? No? Right. Okay. Let's start from start. Okay. Okay, for instance, they are creating a targeted shape. And the child robots moves their targeted areas. For instance, this is the targeted, and we have changed the failed robots. It's kind of fast. Sorry about that. And you can see they know there's a missing robot, and they split and came back here and merge to create that targeted formation. Now they are going in a funnel-like area. So let me stop there. Stop there. I'm not giving up hitting the space. Right. Okay. This is a good example. They created the targeted shape, and they have a formation. They have a task to go from point A to point B. While they are moving, they are having some obstacles in their area. So while the drones are the smaller ground robots locally react and pass by those obstacles. When they have a bigger obstacle, let's say they need to change their global behavior. So they see two different gates. One of them is smaller, one of them is bigger. So they need to decide how to pass, and they need to decide how to change our structure. In this setting, this is the brain robot, and you will see that this brain robot will cede its authority to the other brain robot, because the other brain robot has cameras. It also has cameras. Both have cameras, but the other robot reports that I see bigger gate there, so we should go there. So, and it sees authority to the other drone, and they change their structure to other formation like this, and they pass, and they retain the original formation. Like I said, we don't have enough space to make larger experiments, so we did 200, 300-ish simulation. And we show that our approach is scalable. The conclusion is here. The self-organized hierarchical network actually expand the state of the art in swarm robotics, because we are qualitatively and mathematically analyzable swarm behavior. We had mathematically analyzable swarm behavior, and we can combine that behavior. We have demonstrate this behavior only the formation tasks, because it's much more easy to do some math. So the future approach is expand the other behaviors using the self-organized hierarchical network with other behaviors. And we saw that, like I said, it's kind of quite easy to control and interact with it, because it has a brain robot. That brain robot never dies, because the other robots can claim that role. This is my team, or the team I belong to. Marco Dorigo, Emmanuel Garon. These two guys are my PhD advisors. Weishi Zhu, Mary Catherine Henrik, and Michael Orwright. These are guys to make things happen. Thank you for listening.